Hello and welcome back to California Geology. I'm Dr. Robert Lopez, and today I want to talk about the Sierra Nevada Uplift and the Table Mountain lavas. So looking over here at our PowerPoint, we talked about the subjacent series already and the superjacent series. Now I want to focus on these Table Mountain lavas and what they mean and how they're going to give us clues as to when the Sierra Nevada was actually uplifted, that 9 to 10 million year age I quoted from the previous lecture. Now, this is actually over near Sonora Pass off of Highway 108, and these are called the Dardanelles. And what they are, they're a series of lava flows. You can see some of the columnar jointing in the lava flow here. They're overlying some of the granitic basement rocks down in here. Here's some granite down here. And the idea is that these lavas originated on the eastern side of the Sierra Nevada and flowed from calderas or volcanic centers east of the present crest of the Sierra Nevada and flowed downhill toward the Central Valley of California. In fact, this Table Mountain latite, which is kind of an andesitic flow, this lava can be found all the way down by Knight's Ferry off of Highway 8 down a little bit west of Sonora, the town of Sonora. Now, the idea here is these faults here represent the range front faults of the current Sierra Nevada. And note that these volcanic centers, this little Walker caldera, the origin of these Table Mountain latite, they started here and they flowed down the crest. So one of the problems is how can you get a lava or a volcano, a lava flowing up and over the current high Sierra Nevada. So the idea is when these lavas erupted, there was no topographic barrier. These flows just flowed straight down toward the Central Valley, the Great Valley of California here. Now, here's a close-up of this of that region. So we're seeing Mono Lake down over here. Here's that little Walker Caldera region where these volcanic centers are. And then this important line is the Sierra Nevada crest today. So that's actually the highest point in the Sierra Nevada, the crest. And you can see these lavas are flowing across that crest, right? So especially this original extent of the Table Mountain latite, this one here I want to focus on. And that's the one that starts off over here and flows all the way down. So the Dardanelles are right in here. Here's the Dardanelles. That's the picture I was showing you a little while ago. And it flows all the way down here past the town of Sonora down towards Knight's Ferry, almost in the Central Valley. So obviously, for these lavas to flow downhill, there was no topographic barrier. There was no high Sierra Nevada. That's the consensus right there. So, and the age of these lavas are about 11 to 9 million years old. So at least up to 9 million years, there was no high Sierra Nevada, at least in this region. Although there's another story that's coming up here. We'll take a look. Now, recent work done by Kathy Busby and others over at UC Santa Barbara, they're looking at this idea of this Nevada Altiplano. And in fact, other workers, I think it's Henry from 2009, did some work on some paleo-channels or river channels and which way rivers would flow during the Oligocene time. So the Oligocene time is anywhere from about 23 to about 34 million years ago. So this is well before the uplift of the Sierra Nevada. But you can see from these red lines, these are the old river paths, right? So they're flowing from this high plateau region. So today what the basin and range actually was a high plateau, this almost like this plateau, this high plateau, and then the rivers would flow down toward the ocean over here in the west. And so here we're seeing that trend. And so remember, basin and range faulting really didn't begin to affect California until about 16 million years ago. Now, this little Walker caldera is basically andesitic lava, more of a latite, which has lots of plagioclase crystals in it. There's also volcanic tuff. They're about 9 million years old, and they traveled about 60 miles down the west flank of the Sierra Nevada. The lava flows followed the gold-laden stream beds of the Sierra Nevada. And there are rich placer gold deposits underneath those Table Mountain lavas. And so if you remove the lavas, remove the gravels, you can get to that gold. And later on, I'll talk about hydraulic mining, and that's essentially what they did. and it really kind of destroyed the ecosystem in this region as well. Now, again, Kathy Busby and others had a different idea. Because of extension and tensional stresses occurring along the east side of the Sierra Nevada, one option could be as in the Oligocene time, or before the uplift of Sierra Nevada, time 1 here, we had this plain here, and volcanoes and lavas would flow down in this direction. And then time 2, which is today, we're seeing this uplift due to basin and range extension and the range front faulting occurring here on the east side of the Sierra Nevada. Now, but another idea is that maybe this region of the western United States had always had a high topography, 12, 14,000 foot elevations, this Nevada plano over here, this plateau. And you have the eruption of the lavas, and you're seeing that material move downhill. And recent extension has resulted in these blocks dropping, right? Dropping down. So the idea here for option 2 is we're seeing not that the Sierra Nevada has been really uplifted, it's more like the basin and range has sort of dropped away. And remember, we talked about the geobarometers suggesting that Sierra Nevada may have had a high elevation for most of the Cenozoic era. So anyways, it's probably a combination of both of these. But there's still work being done, right? More research is needed, but nonetheless, what I want you to remember here is that these Table Mountain lavas, they're called Table Mountain because they're flat, represent at least the timing for the faulting to occur in the Sierra Nevada, the range front faulting, which is sometime after that 9 million years, because remember, these traveled from somewhere east of the crest down toward the Central Valley. Now, here's another picture looking at the New Melones Reservoir here in the Stanislaus River here, and we're seeing that these lavas, flat table mountains, note that they're sinuous. They're kind of following the old river channel of the Stanislaus River. So the lavas would flow down existing valleys, and it would kind of create a capstone protecting the softer gold-bearing gravels underneath. Now here's another picture over near Sonora. You can see the nice flat Table Mountain here. So this is an old riverbed with the gravels underneath. And then what happens, here's that same one from a different view. Very nice Table Mountain, sinuous old channels here. So what happens here is, this is a picture from your book, is the lava travels down existing river channels, buries the stream deposits that have the gold placers in them. And then because the lava acts as a capstone, it's a harder rock, it's harder to erode, but the surrounding softer rock is eroded preferentially. So erosion wears down hillsides more readily than the hard volcanic rock. And so we get this inverted topography, where we see the Table Mountains with the old stream deposits underneath. So let's take a look at this one here. So Table Mountains with old stream deposits underneath. Now, this is actually from the Sacramento Bee, published maybe about 5 years ago or so. And here it described making of the Table Mountain. So the lavas flow down the existing river valleys, bury the auriferous gold-bearing gravels down here, stream gravel conglomerate down here. Then here's the lavas coming down. And then differential erosion erodes a softer rock around the Table Mountain, and then in the end leaves this inverted valley. So we often call these inverted valleys or Table Mountains. So that's how they form. And then the new river develops along the side here. All right, so in fact, let's stop here and we'll continue on with the batholith.